I'm going to begin by graphing this exponential function. This exponential function has its variable up in the exponent, and that's why it's called an exponential function. If I start by just plugging in some values and finding some ordered pairs, I could put minus 2 in for x here, and we'd have f of minus 2 equal to 2 to the minus 2. Just putting minus 2 in for x, which would be 1 over 2 squared, which would be 1/4. So when x is minus 2, y would be 1/4. And for the same reason, when x is minus 1, y would be 1/2. When x is 0, y would be 1. When x is 1, y would be 2. When x is 2, y would be 4. So we can plot those dots. Minus 2, 1/4 would be right about here. Minus 1/2 would be right about here. 0, 1 would be right about there. 1, 2, right about here. And 2, 4 would actually be off my graph here, right about there. What we do is we look at the inverse of this function. Now, f of x and y are the same thing, so we can write this as y equals 2 to the x. To find the inverse of a function, we would swap the x and y and then solve for y. Now, the problem is, again, it's very difficult to solve for an exponent, or solve for a variable when it's up in the exponent. So what we do is we write this as a function of x, y written as a function of x, in another form, and it's called the logarithmic form, where the base in the exponent relationship here is the same as what we're going to call the base in the log relationship. Again, this log relationship is nothing but just another way to write an exponent relationship. And the base in the exponent relationship, 2, is the same as the base in the log relationship. Then this whole log is equal to the exponent, y. So the exponent up here is y, and the log is equal to that exponent. And then x here is called the argument. And then we can rewrite y as f of x. So this function right here, this logarithmic function, is the inverse of this exponential function. So I could graph this function by converting it to its exponent form, which would be right here. Again, these two things say the same thing. I'm going to write this in its general form. Y equals log base a of x. That base has to be positive, and it can't be 1. This relationship can be expressed as a to the y equals x. If I'm going to be able to put values in for a, y, and x that'll make sense and not be indeterminate, then a is going to have to be something other than 1, because 1 to any power is still going to be 1. And it also is going to have to be positive, and therefore x is going to have to be positive, because you can't raise a positive value to any exponent and get a negative value back. That value is going to have to be positive. So we can graph this function here by converting it back to its exponent form and then putting numbers in for y, like minus 2 minus 1, 0, 1, and 2. And then figuring out what x is. Well, 2 to the minus 2 is a fourth. 2 to the minus 1 is a half. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. So if I were to graph this, and I'll graph it on the same set of axes here, I'd graph the dot 1/4 minus 2. Now it makes sense that that dot would be on this graph because the dot minus 2 1/4 is on the graph of f of x equals 2 to the x, and they are inverses of each other. That's how we got this thing. So therefore, I should be able to swap the x and y coordinates and get corresponding dots. So we've got 1/2 minus 1, 1, 0, 2, 1, and 4, 2. And here we've got this shape for this graph. And remember that inverses, the graphs of inverse functions, will be reflections of each other through the line y equals x, just like we see here. We note that the x-axis is an asymptote for the graph f of x equals 2 to the x. And since they're inverses, it seems that the y-axis should be an asymptote for the graph y equals log base 2 of x. Now, some properties of logs that are worth noting are that the log base a of 1 is equal to 0. And that's always going to be the case, because a raised to the 0th power is always going to be equal to 1 no matter what a is. So for any value of a to the 0 is going to equal 1. The log base a of a is going to equal 1. That makes sense because a raised to the first power is always going to be equal to itself, no matter what a is. And then if I have the log base a of a to the x, in other words, this base and this argument match, the whole thing is just going to be equal to that exponent. And we can see that by converting this log expression back to its exponent form. It would just be a raised to the x is equal to a to the x. Makes sense? That's got to be true. And then another property is a raised to the log base a of x is equal to x. We can see this by converting this exponent relationship to its log form. We'd have log base a of x is equal to, the log is equal to the exponent, there's the exponent, log base a of x.